So this is a real quick talk, very simple topic. The question was asked of me years ago, what is a delay all about? Is it simple? Is it a constant we can measure? Does it have interesting dynamics? The question turns out to be somewhat yes, somewhat no. So I set out to figure out exactly what is inside of this otherwise boring time series. So what are we doing here? We're pinging things fast, like 10 millisecond probes, 4 millisecond probes, that kind of thing. Small payloads, 8 bytes of payload, plus headers, etc. You can read exactly how we did it. I'm not going to get into methods too much. The interesting results are visual. So what were we testing here? What were we pinging quickly? In this case, some 7513s sitting around on campus with some interfaces donated by a friend's company. We ran tests on a remote site over the public net via a T1 through a 2620 and tested that machine's stack itself and hosts behind it. We tested a Linux machine, previously 4.8, and an NT box. And then also for the queuing questions, for things that we were curious about if could be elicited by high-rate probes just between hosts on campus network. So here's a quick example of a time series with a approximately 20 millisecond probe interval. As you can see, I'm pointing out a couple dynamics that arise in non-uniform link layers. HPNA wireless systems can sometimes change the signaling speed at which the frames are being sent, and the resulting minimum round-trip times are clearly visible. The dynamics of other mechanisms, such as these small spikes and graphs, if you will, are characteristic of other probing activities that the link layer is enacting during the operation of the system. But this is, of course, a fairly simple visual, easy-to-do analysis. There's nothing interesting here beyond perhaps minimums and things you can say that relate to the link layer characteristics. If we do a little bit of work and create graphs that are just more of an overall summary, looking at the frequency domain, we can see a few more interesting things. What I'm showing you here on the left is a picture of about 900, maybe 1,000 seconds of samples at 10 millisecond intervals and a very steep accumulation of time series. We break that into a composite, or I break that into a composite aggregate graph shown at the top with essentially a 0 to 50 hertz span on the x-axis. The y-axis is contribution at that frequency in microseconds. Kind of a small number there. We can see some larger things later. And that is a summary of the entire graph. The entire 1,000 seconds is represented in that single footprint, if you will, fingerprint. The bottom right graph is a rough accumulation of about 200 samples per vertical row or vertical line, if you will. And the z-axis is intensity, from orange being low intensity to purple being high intensity, at a frequency of approximately 0 to 50 hertz from the top of the graph to the bottom of the graph. Again, we're sampling at roughly 100 packets a second, giving us the ability to reveal variations in delay at half of that sampling rate. So looking again at a quick time series, delay is not a simple, constant, boring thing. It appears to behave and have components that relate to things such as the scheduler on the host IP stack in question. We also reveal path dynamics, perhaps that were not visible before, by just asking a router, how deep is your queue? Again, you couldn't ask it quickly enough. It might be better just to send packets and measure the delay and kind of infer that. Some other things that were discovered in this little bit of research were that when queuing events, congestion events, if you will, do occur, they are quite measurable, and they have very interesting characteristics when exposed through a generic time series. This relates to the kind of the ending summary, which will say generally that in these sample sets, most of the data is fairly worthless. Perhaps 1,000th of a percent is interesting, and that's what you're seeing here. Some examples that I've seen across some test runs, the bottom left being the most interesting, showing some sort of a queue resonance, if you will, where perhaps there were several thousand or tens of thousands of multiplexed competing TCP flows that reacted at different round-trip time intervals to apparent loss. So more of the fingerprinting questions, fingerprinting aspects. I thought that was a lot more interesting in this entire bit of research. When pinging a Windows machine with 10 millisecond intervals for approximately 1,000 seconds again, we have a composite spectral fingerprint, if you will, looking like this. 10, 20, and 30 hertz components are dominant, but the grass of the graph is specific and very unique to Windows. Linux 2.4 has entirely different behavior in ICMP or reply times, as evidenced by this spectrum, and FreeBSD, probably the most random and flat uniform of all. Lastly, iOS, generally what we saw on all the boxes, low end to super high end, seems to be an iOS specific thing, less of a line count specific thing. Interestingly enough, we have this grass, if you will, of regular 1 hertz spacings between 10 hertz, let me say below 10 hertz. No other platforms, as you saw here, really exhibit that sort of behavior except for Linux, and they're not necessarily harmonically related. Again, Windows has a similar behavior, perhaps related to a real-time clock that is common to both platforms. So, again, I said this talk is quite short, shorter than most lightning talks will be today. But we can at least ask a couple interesting questions that I guess play more to a research bend to this, or a more academic bend. And that is, when doing this work, the question came up: is network time a thing that is continuous time? I.e., is it a real signal that when we sample it, we should see differences in terms of aliased output? For example, if you sample an analog signal at below its natural components of frequency, or rather below the Nyquist of that signal's requirements, you will see low frequency harmonically related signals being produced as an aliased version of the original signal. We don't see those effects in sampling delay. The more we sample, the more is revealed. We don't see what was revealed change throughout sampling rates, which would mean that if it did change, that the signal is continuous time. But at the same time, the networks don't appear entirely discretized. So what's the correct answer? No one really has thought about this too much from what I can tell. What are we really measuring? Is this just a queue, just a scheduler? Is it all of it at once? Can we easily extract those components? Another one I haven't really thought about, but certainly could be worth checking out. And then again, this is a kind of a strange data set. When we sample things, we only have positive values. There is no waveform per se. There's no sinusoid to this. This is all a random positive going value that does not cross 0. So when we produce Fourier outputs or wavelet outputs, we have a strong 0 hertz component that's a DC offset. How does that supposed to be coupled with? There's some ways I've done this, but does it change the validity of the data at all? That's not been explored. Can this be used for fingerprinting? Natural questions. I think yes. Perhaps this could be a successor to a IMAP or an X-probe of some sort, if someone were enterprising and could incorporate all of the necessary tools and gathering work of fingerprints. And that's all. Any questions? Thank you.